Let us finish our discussion of section 3.1. Last time we discussed solution number 1 of this example. In short, if we have a system of differential equations, one way to solve this system is to solve equation number 1 for x2 and plug in into the second equation. Or method number 2, solve equation number 2 for x1 and plug in into the first equation. In solution 1, we apply method number 1. We solve equation number 1 for x2 and then plug in into the second equation. Note that this is the most natural way to solve the system because equation number 1 is already solved for x2. But now let us apply method number 2. Let us solve equation number 2 for x1 and then compare the answers. So, solution 2. Here is equation number 2 of our system. We divide both sides by -4, done. We solved equation number 2 for x1. Now let us plug in it into the first equation of our system. We replace x1 by this expression, done. When we take the derivative, we can factor any constant out, done. Derivative of first derivative is second derivative. And lastly, let us multiply both sides by -4. Here is the result. Very last thing. If we move -4x2 to the left, we get homogeneous second order linear differential equation with constant coefficients. In solution 1, we already solved this equation. However, in solution 1, instead of x2, we had x1. So we replace x1 by x2. x2 is equal to constant times cosine plus constant times sine. Basically, fundamentally, it's same formula as before. However, to avoid confusions, instead of C1 and C2, I use C3 and C4. Now, it's time to use this formula in this equation. We replace x2 by this, done. We take the derivative. We apply chain rule here and chain rule here, expand parentheses, simplify. This is x1. Now, boldface x is the following matrix column. Component number 1 is x1, component number 2 is x2. We replace x1 by this, we replace x2 by this. Here is the final answer. This is the general solution of our system. Now let us rewrite it in an equivalent way. We can split this matrix column into two pieces. This, which is over here, plus this, which is over here. Next, factor out C3 here, factor out C4 here. And now let us compare the answers. Here is the answer in solution 2. Let us compare this answer with the answer in solution 1. So let me put two pieces together. Over here, we scroll down. This is the answer in solution 1. Let me make it smaller. So solution 2 and solution 1. Note that these two formulas look different. Over here, negative 2, 2. Over here, 1/2, negative 1/2. The formulas look different. However, both formulas are correct. Here is why. Let us continue. Let us factor out 1/2 here, and let us factor negative 1/2 here. As the result, inside square brackets over here, we get sine of 2t, 2 cosine of 2t. Here's why. If you multiply this back by 1/2, 2 times 1/2 is 1, disappears, and sine of 2t times 1/2 is indeed 1/2 sine of 2t. Now compare this with this. Over here, note that if C1 is equal to negative 1/2 C4 and C2 is equal to 1/2 C3, we get same thing. Therefore, despite the fact that these two formulas, formula number 2 and formula number 1, look different, they give us absolutely same result, because C1, C2, C3, C4 are arbitrary constants. So conclusion, on tests, it is not enough to solve a system correctly. In addition, you have to compare your answer with a list of multiple choice answers. And even if you see that there are differences, it is possible to convert one correct answer into another correct answer. We will discuss more examples today. Now, questions.
So basically, do you have to see how your constants can be affected to then equal one of the question or one of the answer choices that are going to be on the test?
Yes, you can say it this way, absolutely. So you look at essential part first, sines, cosines, and then try to adjust coefficients. Well, let us consider other examples. Take a look at this. Note that over here, there is no x2 in equation number 1, which means we cannot solve equation number 1 for x2. Therefore, one way to solve this system is to solve equation number 2 for x1 and then plug in into the first equation. This is exactly what we do here. Here's equation number 2 of our system. Move x2 to the left, done, and then divide both sides by 2. We solved equation number 2 for x1. Now let us plug in this into the first equation. Here is equation number 1 of our system. Let us replace x1 here and x1 here by this expression. Done, done. When we take the derivative, constant can be factored out. Done. We expand parentheses. Derivative of the difference is the difference of derivatives. Next, in order to get rid of 1/2. We multiply both sides by 2. Done. Lastly, move these two terms to the left and collect like terms. Is a homogeneous second order linear differential equation with constant coefficients. We know how to solve it. In order to solve it, we go back to section 2.2. In order to solve this equation, first write down the corresponding characteristic equation. So we replace x2 prime prime by r squared, x2 prime by r, and we replace x2 by the coefficient in front of x2. There is nothing in front of x2, which means the coefficient in front of x2 is 1. Next, we factor this polynomial. Done. Conclusion. R is equal to 1 is a repeated root, which means this is case 2. R1 is equal to R2 is equal to R. In case 2, the general solution is C1 e to Rx plus C2 e to Rx times x. It's exactly what we have here. x2, the general solution of this equation, is C1 e to t plus C2 e to t times t. So here's a formula for x2. How do we find x1? We go back to this. It's over here. We replace x2 here and x2 here by this expression. Done. We take the derivative. Derivative of the sum is the sum of derivatives, and we factor the constants out. Over here we expand parentheses. Since we have minus in front of the whole thing, this plus becomes minus. Now, the derivative of e to t is e to t. In order to find the derivative of t times e to t, we use the product rule. T prime e to t plus t e to t prime. T prime is 1. 1 times e to t is e to t. Derivative of e to t is e to t. Here's what we do next. We expand parentheses over here. Done. And now it turns out that these two terms get cancelled. Same as here. These two terms get cancelled. What is left is just this term. So x1 is equal to this. And now let us put pieces together. Boldface x is x1, x2. We replace x1 by this. Done. And we replace x2 by this. Done. This is the final answer, the general solution of our system. But now, as before, let us rewrite it as a linear combination of two particular solutions. In order to do that, note that over here there is no C1, which means the coefficient in front of C1 is 0. So this can be rewritten as C1 times 0 plus this. Now let us split this matrix column into two pieces. Factor out C1, done. Factor out C2, done. Here is the final answer again. So we have several versions of the same answer. Version number 1, number 2, number 3, number 4. Solution 2. Let me go back to our system. It turns out that we can solve this system in a different way. Note that equation number 1 is an equation of just one function, x1. If we move x1 to the left, we'll get a homogeneous equation of order 1. It's exactly what we do here. Here's equation number 1 of our system. Move x1 to the left. It's homogeneous, first order linear equation with constant coefficients. We perfectly know how to solve it. Rewrite this as x1 prime plus -1 x1 is equal to 0 and apply this formula. This formula is taken from section 1.2. Here is this formula. So we apply this formula where a of t is equal to -1. Replace a of t by -1. Negative times negative is positive. Antiderivative of 1 is t. So x1 of t is c3 e to t. Here, c3 is any real number. So here's a formula for x1. How do we find x2? Now let us plug in this into the second equation of our system. We replace x1 by this, done, and move x2 to the left, done. Now this is non-homogeneous first order linear differential equation with constant coefficients. In order to solve it, we go back to section 1.2 again. First, we find mu. Note that in our case, a of t is -1. We replace this by -1, and the result follows. Mu is e to -t. We multiply both sides here by e to -t. Done. One can check that the left-hand side is the derivative of mu times x2. We integrate both sides, the result follows. So here's formula for x1, here's formula for x2. We replace x1 by this and x2 by this. This is the final answer. But again, as before, rewrite c3 e to t as same thing plus c4 times 0 and split this into two pieces. Now let us compare the final answer in solution 2 with the final answer in solution 1. Let us take a look. Over here is the final answer in solution 1. Again, note that this looks different from this. However, if over here we factor out 2, now we have perfect match. This matrix column is same as this matrix column. This matrix column is same as this matrix column. Therefore, if we replace 2c3 by c2 and c4 by c1, we get absolutely same result. Folks, any questions here?
Will there ever be cases where one way works and the other one doesn't?
No. If we apply method number 1 or method number 2 correctly, we get same answer. I mean fundamentally same answer.
All right,
And
thank
by
you.
the way, if you go back to my website over here and click on PR2, solutions are posted. And for each system, not only I provide 2 solutions, but also in each remark after each solution, I compare answer number 1 and answer number 2. Other questions?
I was just going to say, so on our test, if the problems are done correctly, we should only have to like rewrite constants. Like we wouldn't have to use any like trig identities or anything, or is that not true?
If you look at the posted solutions, you will see that these formulas do not involve any tricks. So you have to manipulate with constants.
Okay.
In other words, not only I expect from you to know how to solve a system, but in addition, I expect from you to know how to analyze this formula. Okay, next. Take a look at this example. Again, we can use method number 1, we can use method number 2. If we use method number 1, we solve equation number 1 for x2 and plug in into the second equation. Here is the resulting homogeneous second order linear differential equation with constant coefficients. This is the corresponding characteristic equation. We find roots. Here is the general solution of this equation. Then we use this formula in order to find x2. We replace x1 here and here by this. Done. We take the derivative, we simplify. Here is x2, and this is the final answer. If we apply method number 2, the final answer again looks different. But now compare these 2 answers. Let me scroll down. This is the final answer in solution number 1. This is the final answer in solution number 2. Note that these answers look different. Here, -3 divided by 2. Here, -2 divided by 3. However, if you factor here -2/3 and here -2, you will understand that both answers are correct. If we replace this by C1 and this by C2, we get same formula. Folks, any questions here?
Can you explain how to transform from one matrix to another one, like step by step?
Basically, the formula is very simple. C1 is -2/3 C3 and C2 is -2 C4. Done. Was that your question?
Yeah.
Okay, let us discuss some other examples. This problem was given on the final exam in fall 2018. The average was pretty good. Let us go over. Method number 1, we solve this for x2, we plug in into the second equation, we simplify, we get homogeneous equation. In order to solve it, we write down the corresponding characteristic equation. We find both roots. These are complex roots. So it's case 3. Here is x1. Now plug in this into this formula, and after all simplifications, there are lots of simplifications, we get x2. over here, x2 is equal to this. We replace x1 by this, x2 by this. We split into two pieces. We factor out constants, done. Now, if we apply method number 2, here is the answer. It is easy to compare these answers. If we replace C1 by C4 and C2 by negative C3, we'll get same thing. So, in this particular case, it is easy to compare the answers. However, take a look at this problem. This problem was given in spring 2019. Averages are much lower. Here is why. If we apply method number 1, we will come up with this answer. For convenience, I copy it here. However, if we apply method number 2, we'll get this answer. And now it is really hard to compare these two answers. Well, here are the formulas for coefficients. But you can say, wait a second, how do we come up with these formulas on a test? Well, let me give you a shortcut. If on the bottom you have the sum or the difference of sine and cosine, this means that we come up with this answer using method number 1. If we have the difference or the sum of sine and cosine on the top, this means that we come up with this answer using method number 2. You may ask me also a question. You can say, wait a second, we compare this problem with the previous one. In both problems, the corresponding characteristic equation has complex roots. How come? Why? In this problem, we have more complicated answer than in the previous one. The answer is, in the previous problem, we managed to achieve really dramatic simplification over here. Many terms got cancelled. After all simplifications, we got only 2 terms here. To the contrast, in this problem, after all simplifications, we have here 4 terms instead of 2. In other words, in the previous problem, the coefficients of our system were chosen in such a way that we achieved more dramatic simplification than in this problem. Lastly, I encourage you to take a look at this problem over here, which was given in summer 2018. The average is really low, and again, same reason. It was very hard to compare answers on the test.
Just to confirm, sir, by method 1, you mean solving for x1. By method 2, you mean solving for x2.
By method number 1, we mean we solve equation number 1 for x2. By method number 2, I mean we solve equation number 2 for x1.
Could you
Yes.
also repeat real quick when to use 1 or 2 based off the summation of sine and cosine?
Yes. So over here, let me go back to this place. If the sum or the difference of sine and cosine is on the bottom, we obtain this answer using method number 1. If it's on the top, method number 2.
Thank you.